In our previous video, we used test-driven development approach to give a very basic implementation for isPrime. And during that process, we saw that our test cases not only guided the implementation, but also acted as guards whenever we did refactoring. And that helped us to ensure that we were not breaking implementations that were working earlier. Let us continue with that practice and give a robust implementation for isPrime. Let's dive in. Here we are back in Visual Studio Code. And as usual, we are here. Only first three tests are passing. The fourth one is failing. Obviously, there is no implementation for that. That's why it is failing. So for any number which is other than 0, 1, and 2, we are returning false, isn't it? So how do we satisfy this test case? Of course, I can do something like this, right? I can say number is equal to 3, return true, right? And pass that test. Of course, some other test is going to break because this is not how we are going to implement, how we should be implementing, right? So this is not the way to satisfy our test. Instead, we should give the actual implementation. So for that, we need to know what is a prime number. So let's recall a prime number. Prime numbers is one that is greater than 1, of course, and does not have a divisor between 1 and itself, right? So if it has a divisor in that range, and it is not a prime number, otherwise it is, right? So how do we express that? Now we will loop through in that range, right? And we will see if there is a divisor. So let's do that. That is the passing number, and like that. So how do we check whether there is a divisor? Simply use modulo operator, isn't it? If there is a divisor, then we are going to return false, right? So we found a divisor. So the number is not a prime number. If there is a number which is a prime, in that case, what is going to happen? You will never find such a number I, right, which can divide the given number. So you will come out of the loop, and then what you should return? Should you return false? No, you should return true, isn't it? Because that is a prime number. Because we didn't find any divisor in the loop. So if we do this implementation, still failing, right? So what is going wrong here? Okay, so definition says divisor between 1 and itself, but it is not inclusive, isn't it? So what is happening here? We started with I is equal to 1. That is the source of the problem. Because 1 is going to divide any given number, right? So always you end up declaring that the passing number is not a prime. So instead of 1, we should have started with 2. Let's see whether this works. Yes, it does work. No more shouting. All our test cases are passing. Looks like all our test cases are valid. It could be the case that your test case itself might be wrong like this, let's say, right? 9983, which is not a prime number, for example. I think it is not a prime number. Yeah, it is not a prime number, but we are saying that it is a prime number. So in this case, actually the logic is right, but what is wrong? The test case is wrong. So we need to be very careful about the test as well. Okay. So let's write it back. So 9973, the proper number. Again, no more assertions. All tests are passing. Wonderful. This might not be the case always, right? You will have to struggle a little bit and you will have to arrive at the answer. Many cases. Here we know about these prime numbers and the logic is quite straightforward. So we could satisfy all the test cases in one shot. But you know what? When you go back and look at this implementation, there is a scope for improvement. Right? Do you really need to iterate up till the number? We all know that from simple arithmetic, numbers greater than half of the given number, they cannot potentially divide the number, isn't it? So it is enough if we actually iterate till number by 2, I think. So let's give it a try. Thanks to the test cases, they are our guards, right? So the moment we make this change, look at that. They come back and shout. Test case is failing here, right? They said, no, 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 one of these tests is failing, right? So what is going wrong? When the number is 4, what is happening? We start with I is equal to 2, number by 2, 4 by 2 is 2. So 2 is less than 2, which cannot hold good, right? So you never enter into the for loop and immediately come out of it and end up returning 2. Because of that, it will claim that number 4 is prime, right? So what we had to do, inclusive of number by 2, we have to check for that as well. So let's add that equal symbol there. So less than or equal. And now try. Boom. The moment we do that, tests are all passing. We are happy. Our refactoring has not broken the implementation. It's still passing. And at the same time, we have made it better. All good, happy. But you know what? There is yet still more opportunity to fine tune this. Right? You don't need to really iterate up till half of the number. What you can do is actually you can use a function called a square root, right? SQRT of the number. If you iterate till here, that suffices. Okay, let's do that. It's working, right? So SQRT is a function which is available in man.h. I had included that, so it is, it's working. If you had forgot to include this, of course, your tests will cry foul and you have to include it. Otherwise, it is not going to work. In my case, I had already included it. That's why it worked, right? But of course, tests can guide you why it is failing and you can go back and fix it. So this is the process of test-driven development. All looks great, but there is one thing, one practice that we were doing. Whenever we found a logical problem in our code, we were going back and doing a manual introspection of the code. And using our intuition, we were figuring out, okay, this could be the problem, right? And we were fixing it. This is okay when we know the algorithms very well and we have good experience with it. But this might not be the case in real world. Functions or your systems might be a little more complicated. And it would be great if it is possible for us to see the program in action and introspect the values of arguments, the values of different variables at a given point of time when it really runs. And that practice is called as debugging, where we use a tool called as debugger. So the practice of debugging is something that we will discuss in our next video. Stay tuned. Thank you.